In this video segment, let us take a quick look at the mechanism behind Matlab's spline function. We'll use this very simple example of a data set with 4 data points as indicated there. The independent variable x takes 4 values -1, 0, 1 and 2, and the response variable f of x or y takes corresponding values 2, 4, 2 and 8. So when x is equal to -1, f of x is equal to 2, and when x is equal to 0, f of x is equal to 4, etc. Now, what spline tries to do is it tries to fit cubic polynomials between successive data points. So these two would be considered as successive data points, these two would be considered as successive data points, and these two would be considered as successive data points, as you might imagine. So it takes 2 samples at a time, and then surprisingly it tries to fit cubic polynomials. Cubic polynomials will have 4 parameters. And what we have been saying so far is if you have 2 data points, at the most you can fit a line. But here they are going to fit cubic polynomials between 2 data points. That means they're going to fit polynomials with 4 parameters for every 2 adjacent points. How do we do that? You can perhaps think of some ideas on how you might make this happen. Basically, you will have to impose certain conditions in order to specify the problem properly. Because we understand this is not magic. You cannot get 4 parameters out of 2 data points. So there must be some interesting add-ons that will help do this for us. Let me start by making this remark that since there are 4 data points, there will be 3 polynomial pieces. So between these 2 data points, there is going to be 1 cubic polynomial. Between these 2 data points, there is going to be 1 cubic polynomial. Using these 2 data points, there is going to be 1 cubic polynomial. So you're going to have total of 3 cubic polynomials. Now let us call the polynomial pieces as P1, P2 and P3. All of them, P1, P2 and P3 are third order polynomials. And based on the previous idea, the first polynomial, the first cubic polynomial P1 is valid over the interval -1, 0. -1 and 0, the adjacent data points. The second cubic polynomial P2 is valid in the range 0 to 1. The third cubic polynomial P3 is valid in the region 1 to 2. So that is what is indicated here. Let's assume that the first cubic polynomial P1 is given as this. So P1 of x is equal to a plus b1 times x plus 1 plus c1 times x plus 1 squared plus d1 times x plus 1 cube. Now there is a reason why we don't say a1 plus b1x plus c1x squared plus d1x cube. We could have said this, but there is a reason why it is written in terms of x plus 1 rather than in terms of x. The reason being P1, the first cubic polynomial, is valid over this interval -1 and 0, including -1 and 0. So when you take x is equal to -1, with this polynomial that has been assumed, x plus 1 will become 0. If x is equal to -1, x plus 1 will be 0. And x plus 1 squared will be 0 and x plus 1 cube will be 0 at x is equal to -1. Therefore, P1 at -1 will be equal to A1. So readily we can find out the value of A1. That's the reason why the polynomials are assumed to be of this form. So there are 4 parameters A1, B1, C1 and D1 that needs to be determined. Now the second cubic polynomial takes this form. Because it is valid over 0 and 1, so at x is equal to 0, this assumed polynomial P2 will be P2 at x is equal to 0 will be only A2. Other terms will drop off at x is equal to 0. So right away we can find the value of A2 to be P2 at x is equal to 0. And P2 at x is equal to 0 is going to be f at x is equal to 0 because we are looking for interpolating polynomials. So you can see the advantage of using this as the second cubic polynomial. The third cubic polynomial P3 will be written like this, involving parameters A3, B3, C3 and D3, and they use x minus 1, x minus 1 squared and x minus 1 cube as the so-called basis functions. The reason being P3 is valid over 1, 2. So if you put x is equal to 1, this term will be 0, this term will be 0, this term will be 0, leaving you with A3 is equal to P3 at x is equal to 1, and A3 will be equal to f at x is equal to 1. So readily A3 can be found out. So that is the reason why it is assumed to be of these particular forms. In any case, you can count a total of 12 parameters that are to be determined. A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. So we need a total of 12 conditions. Only then we can find out these 12 parameters. But how many data points do we have? We have only 4 data points. So we are given 4 clues, but we have to find 12 symbols. So we have to generate 8 more constraints or conditions so that the problem becomes something that is solvable. Let us see how we write the 12 conditions. Please note that the first polynomial P1x at x is equal to minus 1 must equal to 2 because the value of f of x at x is equal to minus 1 is 2. And P1 of x at x is equal to 0 has to be 4. So that will generate these two conditions. Now the second polynomial is valid over 0, 1. So at x is equal to 0 and at x is equal to 1, the second polynomial P2 should match the given tabulated data. So P2 of x at x is equal to 0 should be equal to 4. And P2 of x at x is equal to 1 will be equal to 2. So that follows directly from here. The second polynomial is valid in this region. And therefore, the second polynomial at x is equal to 0 must be 4. The second polynomial at x is equal to plus 1 should be 2. Likewise, for the third polynomial, P3, which is valid between x is equal to 1 and x is equal to 2, the polynomial P3 at x is equal to 1 should be equal to 2, and the P3 polynomial at x is equal to 2 should be 8. So basically, we have these 6 conditions already generated. As you can readily see, these conditions are based on the idea of interpolating polynomials. The interpolating polynomials should pass perfectly through the tabulated data points, and therefore these 6 conditions are there. How do you get 6 extra conditions so that we may make progress? One idea is to make sure that the slope of the different polynomials match at the internal grid points. So here we have x is equal to minus 1, x is equal to 0, x is equal to plus 1 and x is equal to plus 2. These are the 4 values of x at which we have some values of y. Now x is equal to 0 and x is equal to 1 correspond to internal points, whereas x is equal to minus 1 and x is equal to plus 2 are boundary points. So what we are going to say here is at the internal points, we want the slope of the polynomial on the left side to match with the slope of the polynomial on the right side. So for example, if you take the cubic polynomial P1, which is valid between minus 1 and 0, so let's say its behavior at the internal point, which is 0, is like this. We want polynomial P2, which is valid between 0 and 1, also to have the same slope at x is equal to 0. So this is P2 polynomial, this is P1 polynomial. We do not want jumps in the second derivative for P1 and P2. We want them to be very smooth. Therefore, the derivative of P1 at x is equal to 0 should match with the derivative of P2 at x is equal to 0. That ensures smoothness or continuity, as we might call. Similarly, the slope at x is equal to 1 for P2, so P2 is going to, let's say, come like this, that should match with the slope of P3, which is valid between x is equal to 1 and x is equal to 2. We want the slopes of P3 and P2 at x is equal to 1 to match perfectly. We do not want P2 to end like this and P3 to start like that. We are not interested in that kind of a interpolating polynomial. So this is not okay. So this is okay, right? At x is equal to 1, P2 has a negative slope, and at x is equal to 1, P3 has a negative slope, and the slope should also be equal. It is not enough for both of them to be negative or both of them to be positive. We want them to be equal. Therefore, we are able to generate conditions 7 and 8, two more conditions. So the slope of P1 and the slope of P2 should match at x is equal to 0. And the slope of P2 and the slope of P3 at x is equal to 1 should exactly match. Two more conditions have been obtained. We require four more conditions. We can extend this idea that we had for the first derivative to the second derivatives as well. So at the internal points, we are going to say that the second derivative of polynomial 1 should match the second derivative of polynomial 2 at the common point, which is x is equal to 0. Likewise, the second derivative of P2 and the second derivative of P3 should be exactly the same at their common point, which is at x is equal to 1. So two more conditions have been obtained. So we now have 10 conditions. We need two more conditions. You probably realize that we have not imposed any extra conditions on the boundary points, the left boundary and the right boundary. Of course, you could impose some interesting or valid conditions on them as well. We have been focusing on the internal points for conditions 7, 8, 9, and 10. We can also focus on the boundary points and impose two conditions on them, one condition at each boundary point. Now there are many choices. Matlab Spline command may do something else, but other scientists have come up with this particular idea where they set the second derivatives at the end points equal to 0. That means the second derivative of P1 at x is equal to minus 1. This is the left boundary point, and the polynomial that is valid at that point is P1. Therefore, the second derivative of P1 at the left boundary point is equal to 0. Polynomial P3 is what is valid at the right boundary point, which is at x is equal to 2. So they set the second derivative of P3 to be 0. So these provide conditions 11 and 12. Again, we have to note that these conditions that we have imposed here are valid possibilities. Of course, you can come up with other conditions. The broad idea is to estimate the 12 parameters because we are trying to fit cubic splines. To get the 12 parameters, we need 12 conditions. Out of the 12 conditions, 6 are specified by the data itself. That is what you see here. The external grid points give one condition. The internal grid points give two conditions based on the tabulated data. So 6 conditions are there. And the other 6 conditions is our choice. It's our imagination. As long as there is reasonable difference, any extra 6 conditions will be fine. So in this video, we have outlined 6 conditions that have been used popularly by scientists. So with these 12 conditions, the 12 parameters can be computed. Of course, we can do it by hand. This is not tough. So we can set up a 12 by 12 system and we can do the linear regression and get the values of A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. But MATLAB will do it for us. We don't have to worry too much about it. Although we have done this example with 4 data points, you should be able to do this with 5, 6 or 20 data points and be able to communicate to somebody who asks you how the cubic polynomial splines are set up and computed. But now let's look at the Matlab commands. So the first 2 lines of code, I can do it in the command window or in the M file. So I declare the values of X and the corresponding values of Y. And then I use the command pp equals spline X comma Y. By default, it will produce cubic splines. Of course, you can be very specific and tell what kind of spline you would want to fit. So I urge you to try it out. When this line of code is executed, MATLAB will produce the results. As you can see here, this is from MATLAB session. So it produces this result upon execution of this command. So it says pp is a structure which has the following fields. Form is pp. It has breaks. I'll try to explain what it is. These coefficients, remember the 12 parameters, so that comes out as 3 by 4 matrix of coefficients. Double means it is a number. It's a numerical thing with double precision. And then it says something about pieces, it says something about order, it says something about dimension. Dimension is equal to 1, we can understand, because this is one dimensional interpolation. You have one x variable. Therefore, it is one dimensional interpolation. Let's go through these results in detail in the next few slides. So the breaks, what does breaks means? So if I type pp dot breaks, remember pp is a structure and it has these fields, form, breaks, coefs, etc. So if I type pp dot breaks, it will give the values of the breaks. The values of the breaks are -1, 0, 1, 2. Breaks are nothing but the break points. That means points between which the polynomials are constructed. So polynomials are constructed between -1 and 0. Polynomial is constructed between 0 and 1. A polynomial is constructed between 1 and 2. So that's what this breaks means. So if you give me pp dot breaks, I can tell you how many polynomials were constructed and what are the values of x for which the polynomials are valid. When I say pp dot pieces, it comes up with a number 3. Basically, we know there are 3 pieces of polynomials between the 4 data points. So we know it is p1, p2, p3. And the order, right? If I type pp dot order, so there is something called order, right? So I'm looking at this now. pp dot order, it says 4. Basically, it tells us that each polynomial has 4 parameters. And we know we went for cubic polynomials, and cubic polynomials, each of them will have 4 parameters. All right, so that is order. Now, dim, as I said earlier, if I type pp dot dim, it gives me the dimension, which basically indicates the problem has only one independent variable, because this is one dimensional interpolation. As I said, there is only one x variable. The only thing that we didn't look for yet is this coefs. So now I type pp dot coefs and I get this 3 rows and 4 columns as is indicated here. 3 by 4. Double means double precision numbers. So it prints out something like this. And if I just remove the zeros, right, because there are zeros everywhere after the decimal point, so I'm not carrying it out here. So you see this is reproduced here. Now the question is, what do the numbers mean? You can imagine what the numbers mean. I'll explain it in the next slide. The first row, as you would have imagined, stands for P1x. The second row stands for P2x. The third row stands for P3x. This is something we could have imagined, given that we knew there were 3 polynomials and each polynomial had 4 parameters. So we knew that 3 by 4 came from that kind of a information. The first row stands for P1 of x, and if you put the values 2, -8, 8, 2. So 2, -8, 8, 2. 2, -8, 8, 2. So it is going to be 2 x plus 1 cube minus 8 x plus 1 squared plus 8 x plus 1 plus 2. So it starts from the highest polynomial power and goes till the constant term. So it is basically this. So the numbers are written in the order D1, C1, B1 and A1. So this is D1, C1, B1, A1. D2, C2, B2, A2. D3, C3, B3, A3. So P1 of x is this. You can check. When you put x is equal to -1, you're going to get 2. Only this term will survive. And if you look at the table, you know that f at x is equal to -1 is 2. So that's good. When you substitute x is equal to 0 in this expression for P1, you're going to get P1 of x at x is equal to 0 is 4. And that matches with the value of f at x is equal to 0. So that's good. The second row gives us the coefficients for the second polynomial piece, P2. So the numbers read 2 minus 2 minus 2, 4. So 2 minus 2 minus 2, 4. So this is, as I said, D2, this is C2, this is B2, and this is A2. So it does it in the reverse order of how we represented it, right? So just be aware of it. And you can check for the values of P2 at x is equal to 0 and at x is equal to 1. It matches with the tabulated data. So P2 is an interpolating polynomial for the domain x is equal to 0 to x is equal to 1, as was P1 for the domain x is equal to minus 1 to x is equal to 0. The third polynomial piece, 2, 4, 0, 2. So this is the coefficient of the highest power. This is for the second highest power, the third highest power, the constant term. So 2, 4, 0, 2. So 2, 4, 0, and 2, starting with the highest power. So this is P3, and you can verify that P3 is an interpolating polynomial. What we get is that spline command can help get the spline polynomials, which are all interpolating polynomials, and we looked at the theory behind it. That's the most important thing, how people thought about this problem. They did not want to fit lines between successive data points. That is the easier route. They want smooth looking functions for their system. Therefore, they adopted this very clever approach along with interesting mathematical conditions based on what they have seen in the physical world, right? How systems behave, etc. So motivated by that, they said these mathematical conditions are valid and they can be used to exploit higher order interpolating polynomials. Now, if you wanted to know the value of f of x at x is equal to 0.5, we should use P2, because P2 is valid between x is equal to 0 to x is equal to 1, and the query point is x is equal to 0.5, which falls in the domain of P2. And therefore, if you use P2 and you evaluate that at x is equal to 0.5, you will get the value of 2.75. You can also use the Ppval command in Matlab. So Ppval, the PP structure that you have determined using spline command, you give the query point, the x value for which you want the f of x value, you get 2.75. I hope you got a glimpse of how splines are constructed. Thank you for your time.